Now, before we dive in, let me explain how I've organized the topics of this course. There are three major parts or units. These units reflect three different ideas about what a computer looks like. Now, to explain what that means, let's go back to CS 101. There, you probably learned about a machine model called the sequential or serial RAM model. There's a single serial processor connected to memory. This processor issues instructions that operate on data. The operands of these instructions always live in memory. When you analyze the cost of a serial RAM algorithm, you assume that all instructions have a cost that is bounded by some constant. Now, from that starting point, you do a big O-style analysis in terms of the input size. So that's the serial RAM model. I hope you already know it by heart and maybe even love it a little. Now, what are the alternatives to the serial RAM model? Well, a first alternative is the parallel RAM or PRAM model. Instead of one processor, there may be many. They all see the same memory, and you still assume a bounded constant cost per operation, but you get to work with more than one processor. And since the processors all see the same memory, they can coordinate and communicate by modifying shared variables. Now, in this model, your algorithmic analysis will involve big O's as before, but you'll try to reduce the total cost by up to a factor of p, the number of processors. A PRAM-style model is arguably the simplest one that you might use on, say, a shared memory multi-core machine with uniform memory access. Who's what's it? Don't worry, you'll get there. So that was one alternative. Here's another, a distributed memory network model. It's basically just an interconnected network of RAMs. That is, you start with multiple RAM computers. Each computer is a processor with its own private memory. No processor can read or write the memory of any other. Instead, they join forces, connecting to one another over a network. They coordinate by sending and receiving messages over this network. Now, in this model, your analysis will count the number of messages and the total volume of communication. Okay. Now here's a third alternative that we'll consider in this class. It's a two-level input-output, or I/O model. In this model, there are one or more processors connected to a main memory. It's sort of like RAM or PRAM, but you assume that there's at least one level of fast memory that sits in between the processors and the slower main memory. This model forces you to think about the following question. How much data needs to move from memory to the processor using this small but fast intermediate memory as scratch space? Now, if you know about things like caches or virtual memory, then you might already know this basic model. But even if that's the case, do you also know how to design algorithms that exploit it? So, to recap, we will discover the big ideas of this course using three machine models: the PRAM, the distributed memory or network model, and the two-level or I/O model. So with that as background, I think we're finally ready to start. Woot!